Wonderful. My name is Linda. I'm an author. I'm an illustrator. I'm an enthusiast-level programmer. And I'm a business school dropout. And today I want to help all of you to rekindle your excitement around technology. I'm the co-founder of an organization called Rails Girls that teaches young women programming all around the world. And the first language I fell in love with was Ruby. Ruby, the programming language, allowed me to express myself in ways that I didn't with PHP or HTML or CSS earlier on. But there was still this hurdle of learning to express myself in this language. So I would study all of these books, and every time I would run into something I quite didn't understand, I would try to imagine how would Ruby, a 6-year-old little girl, explain what is object-oriented programming or what is garbage collection in mobile development. And I feel at that point, 6-7 years ago, something in my brain irrevocably switched. You know how there's people who see numbers as colors? I started to see the world of technology as stories. So I imagined that, okay, if there's a fierce 6-year-old little girl called Ruby, what if Apple, the company, was a character? It would obviously be the snow leopard who's beautiful but doesn't want to play with the other kids because they are too messy. It likes only well-designed, beautiful things. And if Linux was a character, it would obviously be the penguin who's really, really efficient and good at like getting problems solved, but somewhat hard to understand at times. And there would be the idealistic Firefox and Django with his pet Python. And I came up with this whole array of characters and stories around the world of technology. And then I go to my mom and I tell her, Mom, I have this idea for a children's book. And she says, that sounds horrible. That sounds like a 70s Soviet propaganda book. Why on earth should kids understand how the big technology companies in the world think? Well, the reason for it is because technology companies, they touch billions of lives. Governments can't reach billions of people. Religions barely reach billions of people. But these big companies, they reach billions of people on a daily basis, and they are not neutral. But I figured something about the feedback was probably right, and I started to think, we all know how programming languages share actually a lot from one language to another. All programming languages have similarities, like most of them have variables, most of them have some sort of arrays or list structures to hold those variables in, most of them have functions. What if I ought to teach kids programming before the syntax? What if I could teach these thinking structures of programming prior to touching any code? And I kept thinking and thinking, and I figured that, okay, if code is the next universal language, instead of grammar classes, we ought to be teaching kids poetry lessons. And what I mean with that is that we don't learn Finnish by only conjugating the irregular verbs like minä syön, sinä syöt, hän syö. We learn a language by speaking it. We learn a language by writing bad poems and essays and articles. And even though programming languages are not natural languages, if we are serious about attracting a far more diverse group of people into this magical world of programming, we ought to be offering them more poetry lessons, less grammar classes. And I think we live in this golden era of learning to program because we have so many wonderful tools and services. On the other end of the spectrum, we have things like code.org, which offers these puzzles and gamified experiences around learning to program. On the other end of the spectrum, we have things like Scratch, wide room and a big playground for kids to experiment with. But the question I had was, where do stories fit into this equation? Because after all, aren't stories the way we humans have always understood and learned about the world around us, about ourselves, and about each others? Why is no one telling stories about the world of software? So here's Ruby. She's 6 years old, completely fearless, a little bit bossy, and when Ruby's dad tells her, Ruby, we're running late from school, you need to dress up really quickly. Ruby does dress up, but she leaves her pajamas on because dad didn't specifically first ask her to take the pajamas off. And when Ruby is told that, oh, Ruby, your room is a mess, clean up all the toys. Ruby cleans the toys, the Legos, and the building blocks, but she leaves the pens and papers on the floor because, Dad, come on, pens and papers are not really toys. And there is a chance that I'm raising the most obnoxious generation of kids ever. But I'm also teaching them something very profound about how to speak to a computer. Namely, you need to give very exact commands. The instructions need to take into account all sorts of situations. The commands need to happen in the right order. And maybe most importantly, that even the biggest problems in the world, they are just tiny problems stuck together. And that's the thing I'm most jealous about for engineers, that attitude that you can solve any problem in the world if you just make it into many tiny small problems. Turns out none of this is really new thinking. I spoke with the people who understand play best in the world, and those people come from the same latitudes as I do, from Copenhagen or from Denmark, from Lego, and they showed me this fascinating chart about different motivations of play. They say that there's 3 basic types of motivations. There's achievement-based motivation for play, there's social motivation, and there is immersion motivation for play. But for some reason, whenever we're teaching kids about coding, we're only talking about achievement. We're talking about challenging each other. We're talking about provocation. We're talking about domination, gamification. Whereas everyone here who programs knows that there's so much more to programming. There's the joy of finding a new answer to a problem that you didn't know how to solve in the past, a new way of solving a problem. There's the joy of giving and receiving help from others. And at least for me, there's the joy of escaping real-world problems. So in some ways, I was thinking that, okay, I'm going to teach programming through stories, and I'm going to teach programming through all the different aspects of play. And none of this is actually, again, very new thinking. Any here, the people who've studied pedagogy know that Jean Piaget already in the 50s stated that you can't teach a new discipline for kids only by giving them a pre-ordered vocabulary of concepts. Learning is grounded in action, and somehow we need to take these high abstract words of computer science and make them tangible and real. And that requires us to do some very uncomfortable things, like ask questions that computer scientists don't normally ask. Because as computer scientists, many of you are familiar with asking questions like, can you define what a loop is for me? The definition of a loop. But a rather more poignant question might be, how does a loop feel? And this is the way we attract kids who are not naturally interested about analytical and logical puzzles into the magical world of computers. So how does a loop feel like? With kids, we practice the concept of a loop, the idea that a computer is really good at repeating sequences over and over again by having a real-world dance party. So Ruby's favorite dance move is clap, clap, stomp, stomp, clap, clap, and jump. Ooh. And we practice a for loop by repeating the dance sequence 5 times. We practice a while loop, so the kids keep dancing while I'm standing on one leg. And finally, as homework, they get an until loop. So they keep repeating the dance sequence until mom gets really frustrated. And in this way, I hope the kids get a very kinetic experience of what a loop feels like. Then they might go on to visual programming languages and build out of building blocks that loop. And then they might tackle coding. And very importantly, I think we need to be giving context, like why are you learning this abstract concept of a loop? Well, because if you want to write a game, you probably write a loop that says, keep moving the hero until it hits the enemy. And this is work that the computer science industry hasn't done, because it's been enough that we attract us here in the room into this industry, but it's not enough in the future. So it turns out there is this whole field of study around these thinking skills that you learn prior to learning the syntax of coding. And those skills are called computational thinking skills. And they include concepts like decomposing a problem, thinking algorithmically, logical and critical thinking, but they also include practices like collaboration, persistency, the ability to debug problems. When I started this project 4 or 5 years ago, I had no idea of this theoretical background, but I had a strong vision of a world that I wanted to be a part of. A world where it would be okay to be a little girl who enjoys stories and imagination and play, but also gets really excited about computers, because that's the kind of a girl I was. And I put this project proposal online on Kickstarter, which at the time was still a fairly small thing. And I figured that I've met enough Ruby parents all around the world who are equally excited about this vision of a world. And in the first 24 hours, the book project gathered almost $100,000 worth of pre-orders from all around the world. And in the 30 days that this book was online, available for pre-order, it gathered almost $400,000 worth of pre-orders. It also represented 20% of the annual book exports of the entire country of Finland. And at this point, I had never done a book before. I had never illustrated a book before, and I didn't consider myself to be an expert in computer science. So you can imagine that for the past 3 years, it's been kind of a whirlwind experience learning all of these skills as I've gone. Well, today Ruby is published in 23 different languages. In Australia, my publisher is Penguin Random House, and it's actually grown into something more than only teaching kids about programming. I've written a book about how computers work. I've written a book about how computers talk to each other, the networks, the internet, and now I'm writing on a book about artificial intelligence and machine learning, and what should a 6-year-old understand about that world? I think the reason all of these topics are so fascinating and important is actually twofold. A few weeks back, I read this UK article from a scientist who says that kids know Bulbasaur better than Badger, which goes to say that kids recognize more Pokemon species in the world than natural animal species. They have a better grasp of this universe of Pokemon than about birch trees or badgers. And the writer was obviously a little bit worried about what happens to a world where we don't have words to express the things we see around us, where Finnish kids don't anymore have 7 words to express the snow we get or fall, or Australian kids something else that your wonderful and magnificent nature provides you. But I would argue the opposite also. What happens to a world where more and more of our world is surrounded by technical concepts that most of us people don't understand? What happens to a world where we casually throw up things like DDoS attack or denial of service attack, but most of us don't have the pretext or the concepts to explain these things? These words of computer science are black boxes. They hold a lot of information inside of them, but they let very little out. And I think it requires us to ask, again, questions that we haven't asked before. Like, how do you explain what the internet is for a generation of kids who have never clicked the disconnect button, whose internet is all around them every day, all the time? Well, how do you explain it? Is internet the hardware, the servers, and the wires that go from the bottom of the sea to the space? Is internet the protocols, the PCs, packets of data that give instructions on the software on how to move on the routers? Is internet the impact, the people, the cat videos we watch all day, every day? Well, it's all of them, and this is the challenging thing about doing this new kind of technology education for kids, because again, technology is not good, it's not bad, it's not neutral. It's multifaceted, it's everywhere, and we need to explain really complicated and big concepts in an approachable manner. And I think more than teaching kids coding, I think my mission today is preparing kids for a world where more and more of the problems around us are computer problems, but we're not going to solve those problems with only the engineering brain of the current population. We need a far more diverse group of people thinking about what kind of problems we ought to be solving. So here's a confession. I'm really jealous for the people who grew up in the 70s here, because you had this different, tangible relationship with computers. You could actually touch a transistor. That's amazing. For my generation, you can jam 300 million transistors at the pinpoint of a pen, and there is no way of describing anymore how a computer works. We have these machines that are more powerful than the machine humankind went to moon with, that fit our pockets instead of this stadium, but we don't know anymore how they work. And sometimes I wish that I could kind of shrink myself to the size of a silicone chip and kind of get this tangible feeling of how a computer works from the inside out. Unfortunately, that's not possible unless you're a children's book author. So that's exactly what I did with little Ruby, plunging her into an adventure. So one day Ruby is really, really bored, and she goes into Dad's office and she types her password to the computer, but the computer doesn't work. All of a sudden, the white mouse wakes up next to Ruby and says, "Oh, Ruby, I've lost touch with the cursor. Can you help me find the cursor?" And Ruby says, "Oh, of course, I'm the best computer debugger I know of. Let's figure it out." And together, they make themselves really, really small and crawl inside of the computer and fall deep, deep inside to the layer of the electricity, where there's billions of tiny bits that only know how to go on and off, on and off. And Ruby and Mouse think, oh, it's going to take too much time to figure out where the cursor is. If we're going to deal with the bits, we need to go higher. So they meet the logic gates that take those bits and combine them in different ways into more complicated math structures, but they only know how to ask puzzles, and Ruby's not really into that stuff right now. So up they go, and they meet the CPU, the processor of the computer that is really good at giving commands to all of the other components, but really forgetful, so it needs the help of the RAM and the ROM and the hard drive to remember things. And they meet the GPU that is in charge of creating these wonderful images on the computer, and also really fashionable nowadays. And they go dancing on the operating system, and I'm not going to spoil you how they end up finding the cursor, but they do find the cursor eventually. But I think even more importantly, they get this profound concept of a computer from the lowest levels to the highest abstraction levels. And I think this is very, very important for a generation of kids whose computers will look nothing like the computers you and I grew up with. A computer can take 1,000 forms and have 1,000 faces. And today, computers are digital, but tomorrow they might be biological, they are theoretical, they are physical. And I think giving a fearless and brave attitude around computers for kids is one of the most important things we can do as parents and educators. For me, one of the most fascinating moments in my journey of computer science was the moment when I realized how computers actually do this trick. How electricity turns into logic, how logic turns into hardware, how hardware turns into software, and how software turns into the apps we know today. And it all starts with these three fellows, the logic gates. And I knew on a conceptual level what a bit is. I could follow along the idea that a bit is a switch that goes on and off, on and off. It's electricity there, electricity not there. It's 1 or 0, it's on or off. But I had a hard time understanding what happens next. How do these bits make it inside the computer? So that's where the AND gate comes in. So when Ruby meets the AND gate, she tells the AND gate, "Hey, I'm Ruby." And she tells, "I just fell in a puddle." And she gives the AND gate two statements. I'm Ruby. So I'm wet and I'm cold. And the AND gate always gives out "that's true." This is another way of saying it, but the computer scientists like numbers, so we're going to use ones, ones, and ones. So if you give two true statements for the AND gate, out comes a true statement. If Ruby tries to be a little bit sneaky and cheeky and give one true statement and one false statement, like, "Hey, AND gate, I'm warm and I'm wet," the AND gate says false. And here's another way of doing the same thing. And here are all the different options the AND gate has, and here's the way mathematicians would say the same thing. So that's the AND gate. The OR gate, the second gate, is a little bit more relaxed. Even if one of the statements you give for the OR gate is true, out comes a true. A little bit more relaxed. And here's the mathematical way of doing the same thing. And then finally, we have the NOT gate. This is the favorite of the kids whenever I present this, because it always inverses the thing you say to it. So if Ruby says, "I'm warm," the NOT gate says, "You're wet," and so forth, and so forth. And here's the way of doing the mathematical version of it. But this still didn't bring me to the idea of, like, how does this relate to electricity? What's the connection here? Why am I doing these stupid little truth tables? And why am I working on this stuff? And in order to get here, we need to meet a guy called Claude Shannon. And Shannon was a mathematician, electrical engineer actually, who happened to study philosophy in his undergrad and ran into this work by George Boole, this eccentric English philosopher. And then he happened to notice something funny with the electrical circuits. So Shannon realized that this is how you wire electricity circuits. When the gates are open, the switches are open, there's no light. When the switches are closed, there's light. See? No light, light. And he noticed that, there's something similar with the AND gate and the electricity circuit. Wonder if this happens with the other gates too. And he noticed that this is another way of wiring electricity too. And here you remember how OR gate was a little bit more relaxed. Even if one of the gates is true, the electricity still flows inside of the circuit, and the OR gate is happy. And I remember seeing this and thinking, oh boy, oh boy, oh boy, having this like gigantic like head whirl and realizing that, oh wow, this is how computers are made, of tiny electrical switches that go on and off, on and off. And I had read that sentence 100 times, but it never like made itself clear to me before I made this little narrative and story. And by combining the different gates, you get more complicated gates. You get adders, you get the processor. By combining different materials that conduct or don't conduct electricity, you get different hardware components and chips and stuff like that. And I think the idea that our kids would have this experience, not that they would need to be able to explain exactly what happens inside of a computer, but get this idea of a computer as an abstraction machine is something that I wish kids around the world would have a chance to experience the same excitement I had. Not, again, that they would need to explain what a computer does, but one of the exercises I really personally like doing is this exercise where I ask kids to imagine what is inside of a computer. And I imagine if I were to do the same exercise with many of you, a lot of you would return an empty page for me, because this is the thing with us adults. We feel we're not experts, even though this room is full of experts in computers, but maybe you feel like, oh, I'm not a computer architecture expert, I only do the front-end stuff, or I'm not an expert in the electricity layer, I only understand this or that. But the cool thing about the kids is that they come up with hypotheses. Even though they have no idea how a computer works, they come up with a hypothesis. So I've seen kids who describe computers as content containers. They describe that computers have files and apps and games inside of them. That's true. Computers are content containers nowadays. I have kids who describe computers as these abstract networks of interlinked components, and I think these are the future architects, or the computer architects, and that's true too. This is a way you can describe a computer. I've had kids who have these sort of anthropomorphical explanations of a computer. They describe the computer as a theater stage and each component having their own role. Those are cool kids. I do the same thing myself. I even have kids who have this very steampunkish idea about a computer. They imagine that there's little gears inside of a computer, and they might not be right. There's nothing mechanical per se inside of a computer, but they grasp this idea that a computer is made of these very tiny, dumb pieces that altogether form something bigger. And then my favorite kids, the kids who make a stab at drawing the computer, who draw transistors and draw the electricity and draw the interlinked components. But I think most importantly, the kids who understand that while a computer is magical, it's not magic. While a computer is magical, it's not magic, it's based on logic. It's something that us humans created. It's not a black box. So the next step in this exercise, and again, the kids are around 6 to 7 year old when I do these exercises with them, is one where we build a computer out of paper. And the kids cut out the different components of the computer and put the CPUs and the RAMs and the ROMs inside of the computer, and you can see how proud they feel about the first computer that they created. And pretty soon they start creating apps for their computers. And the first apps are always replicas of things that they've played. I've seen so many Angry Birds like replicas out there, but quite quickly, the kids get into this mindset of creating rather than consuming. So I had this little boy who was completely immersed in his paper computer. He had these huge headphones on because, you see, he had built an intergalactic planetary navigation application on his paper computer because his favorite thing in the world was to be the mission control man to his father, who was the astronaut far away in the Martian orbit, but really on the other side of the room. And the boy's role was to bring Dad safely back home on Earth with his tiny paper computer. And I think experiences with technology like these that don't necessarily require the newest or fanciest machine will pave a way, a more creative, a more fearless way towards technology for the next generation. But the challenge is computers, again, they won't look like the computers you and I grew up with. I often show the kids between 6 and 9 years old these 4 pictures. I show them a picture of a car, I show them a picture of a grocery store, a dog, and a toilet. And I ask the kids, which one of these do you think is a computer? And the kids, who we think are so creative, so out-of-the-box thinkers, they cross their hands like this and they go, Linda, you're completely bonkers. None of those is a computer. Computer is the glowing box which in front of mom or dad spends way too much time, which is sad. But then we get to talk and we realize that actually a car is a computer because it has a navigation system built inside of it. Grocery stores, they have so many different kinds of computers. They have the teller's machine and the burglar alarm and the ice cream box that keeps the ice cream cold. That's probably a computer. Dogs are not computers, but many kids bring up robot dogs nowadays, and we talk that maybe a dog's collar, it might have a computer inside of it. That would be really neat if the dog is prone to running away. And don't do this if you have kids under the age of 9. But I tell the kids that, in Japan, toilets are computers, and there's even hackers who specialize hacking those toilets. That's like a mic drop moment. There's nothing else you can get done throughout the rest of the day. So we figure out that there's actually hundreds of computers in every single home, because your microwave is a computer, your remote control is a computer, your doorbell is a computer. And the next step in this exercise is one where I give kids these little tiny stickers with an on-off button on them. And I tell the kids that, for this afternoon, you have this magical ability to make anything in this room into a computer. And I've collected these like grocery store, these tuna cans or keys or like glasses or everyday objects on the table. And the kids look at me and they look at the objects and they say, Linda, this is too difficult. I don't know the right answer for this question. And I tell them, you know what? Neither does your parent. They might have just heard about this Internet of Things thing, all the IoT, but it's you who is going to grow up in a world where your toothbrush is a computer and your teddy bear is a computer, and it's up to you to design and build that world. You guys are going to be the last generation of kids that remembers the computer as the glowing box, the screen generation. The next generations are going to remember the computer as something that is embedded all around us. So a little girl comes to me, and she's taken a bicycle lamp. And she comes to me and shows the bicycle lamp, and she says, Linda, if this bicycle lamp were a computer, we could go on a biking trip with my father. We could sleep in a tent, and this bicycle lamp, it could also be a movie projector. And that's the moment I'm looking for. Not the moment when the kid understands the differences between hashes and arrays in Ruby programming language or writes an if-else statement in JavaScript. The moment when they understand 3 very profound things that even as adults have a hard time remembering. First of them is that the world is not ready yet. There's so much we haven't invented or discovered or created yet. And there's this sci-fi writer who says that everything that happens in technology before you turn 30 is natural and like according to the order of the world. And everything that happens after that is unnatural and weird and suspicious. And I'm 31 right now, so I'm studying myself very closely and seeing if I'm forgetting that there's so much we haven't invented in this world yet. The second thing the little girl realized was that technology is a wonderful way to make the world a little bit better because it scales and it creates wealth around it, and technology has been the way humanity has always advanced. And the third and the most important thing was that for a moment she had the self-agency, the self-efficacy and the self-belief to believe that she could be the world's first movie projector bicycle lamp inventor. Odds are she's not going to be the next Steve Wozniak or the hardware hacker of the future, but I think that moment is the moment we ought to be shielding in childhood and a little bit in our own adulthood too. I think far more important than teaching kids to code is actually giving them a robust sense of what a computer is. And to help in that, there's another concept I want to introduce you, which is called the notional machine. The idea of giving a mental model for kids to understand, and adults too for sure, of what a computer is good at and what a human is good at. And it requires, again, us to ask those uncomfortable questions. Can computers have sensors? Sure. But can computers sense things? Can computers have feelings? Those are questions that we used to know the answers for, but especially now with the NIPS conference going, like, let's see what kind of answers we get out from there. And in order to explain what a computer really is in the future, we actually need to look to the past. So we need to look all the way back to the year 1945 when John von Neumann came up with his input-output concept, the von Neumann machine. And for those of you who are a little bit rusty on your computer science history lessons, basically what von Neumann said, that a computer is any device where you put in data, you modify the data somehow, and out comes the modified data. And this is true if you go on Facebook and like a post, in goes the updated like count, in goes the knowledge that someone has liked this post, out comes the updated like count. But this is also true when you sit in a car and you forget to buckle your seat belt. In goes the data that someone is sitting on the seat, out comes the beep, beep, beep thing we hate so much. And the cool thing about the world is that, unlike in von Neumann's time, we have so many different kinds of input-output devices. We have so many different kinds of sensors collecting that data. But the thing that is still true from von Neumann's machine is the memory. And von Neumann came up with a stored memory concept, and he says that basically computers have two types of memory. They have the memory that remembers the data that comes in and the modified data that goes out. But more importantly, they have the memory where you type in the instructions on what to do with that data. And that's what makes computers so special. Because a pinball machine can only be a pinball machine. A tractor can be only a tractor, but a computer can be anything based on the instructions you give for it. So at this point, the kids are usually really like, let's do something. You've talked for a long time, so we build an input-output machine. The kids crawl inside of the computer. There's a tiny piece of instruction, like come out jumping on one leg, and the kid comes out jumping on one leg, and the other kids need to decipher what happens inside of the computer. And this input-output machine is so fast that it usually ends up breaking after a few rounds of processes. So what about the data? There is so much data in the world, partly the data we create and partly the data that is gathered from us. And one of the things that really makes me sad personally is the fact that we again use very abstract big words to describe this data. And we make it very unapproachable and very like a black box again for the rest of the world. So an exercise I like to do with kids is one where I ask them to write 3 things about themselves on a piece of paper. I ask them to write a video they've watched recently, a place they've been with their phone, and one thing they've liked or given thumbs up to online. And they have these 3 little pieces of paper. And with tiny, tiny clothespins, we attach those 3 pieces of data on their clothes. So it might be someone who's liked a turtle video, who's visited Brisbane, and who's liked a Lego building block set on Instagram. And then I tell the kids that this is a tag your it game. We're going to choose Facebook, Microsoft, Amazon, and Google among you. And those kids are going to run around and try to gather as much data as they can from your clothes. And you lose when you lose all of your data. And obviously, at some point, everyone loses. But we have this beautiful big pile of data at the middle of the room. And the kids need to go there and pick a new persona. So maybe someone who's liked a My Little Ponies video and who's been to Melbourne and who has liked a Beyoncé video. And the next step is I give them the front page of a newspaper where I've blocked a few titles, a few ads, and a few pictures. And I ask them to redesign that front page for the persona they've just created. And then we get into really interesting discussions about how do computers know what to show to you? How might it be a good thing that everything you see online is tailored to your likings and your preferences? And how might it be a little bit of a dangerous thing? And the interesting thing here is that when I was, again, explaining this concept to my mom, she looked at me like this, and she's like, so it's not an accident Facebook knows which dress I was watching earlier in an e-commerce site. I'm like, no, Mom, it's an algorithm. And I think it's fascinating how given we take all of these concepts when we ourselves have a technical background, where we are allowed to peek inside and understand what happens. But for the rest of the world, these concepts are just things that they take for granted. Like, of course, computer science is magic. It's not magic, it's magical. It's based on logic. And far, far importantly, I think the kids of today, they will have their first experience with artificial intelligence, with machine learning, far before they can write, far before they can read, probably far before they can actually speak. And making these concepts approachable and understandable for this next generation is our responsibility. I would far more far more to have a pragmatic and optimistic generation of kids who don't partake in the fear-mongering around AI, who don't think that singularity is going to arrive any second now, who don't say that artificial intelligence is going to destroy our planet, who know that, for instance, when it comes to self-driving cars, the input is the cameras that the car has. There's a process that maps that camera data into a map where the other cars are located, and the output is that map that the car can use to navigate. So a pragmatic and optimistic relationship with technology. And these are small experiments I've started to do around machine learning and AI, trying to teach kids about how do you learn this new paradigm of programming that even as adults are kind of grasping currently. So how is machine learning different from the stuff that we used to do in the past? Is this a cat? How many here think this is a cat? Yeah, we're kind of uncertain about this. This is the neon cat, by the way. If you haven't seen it, don't watch now. It's an annoying video. So the traditional way of programming would have been to give the program rules and data to describe cats in different ways, and write an algorithm, and out comes the answer. The machine learned way of doing things is give the computer the answers, give the computer a trained set that describes these are cats and these are not cats, give them the data and the answers, and out comes the rules, the computer's own way of figuring out what is a cat and how does a cat look like. And again, this is such a young field that I think there's a lot of room for us to make it more approachable, more whimsical, more colorful, and more fun for a whole new generation of learners. So one final example. My favorite exercise in this world is an exercise I like to call the art machine. And it got started by a little boy who I met in London who came to me and said, Linda, what kind of a job will I have, because the robots will take all of our jobs? And I'm like, oh boy, there's been some serious dinner discussions in this little kid's household. And this exercise was kind of an attempt to try to explain to him what kind of jobs we'll have. So it starts with an algorithm. The kids all get their own algorithm, and we adults tend to think that an algorithm is a scary word. We think about finance and we think about Facebook, both very scary things. And for the kids, an algorithm is a wonderful word. They think it sounds fun in their mouth. It's a big, chunky word. And they, after all, know that an algorithm is just a step-by-step sequence to solve a problem. So an algorithm could be to draw a red circle. An algorithm might be to draw a green dot inside of each red circle. An algorithm might be to connect the green dots with a blue line. And when I turn this computer on, each kid starts to go around and around this big piece of paper with a pen, and they start executing their algorithm. And sometimes the computer goes fast, and sometimes it goes slow. And in roughly 20 minutes, we've created this beautiful piece of artwork. And we all stand up next to the artwork and observe and like feel proud of ourselves. And I asked the kids, so by the way, how long do you think it would take a computer to create an artwork like this? And the kids, they look at each other. There's roughly 10 of them, and they think it took us 20 minutes, so maybe for a computer, 200 minutes, because there's only one computer. And I tell the kids, you know what? It would probably take the computer a microsecond to generate 1 million of these, because this is exactly the kind of task a computer is good at. It's good at repeating instructions, sequences of instructions over and over again, faster than any human could, without making any mistakes like we did. But how does this artwork make you feel? And a little girl says, it makes me feel very busy. And another one says, it makes me think of last summer and the summer holiday we took with my family. And I tell them that, by the way, these are things that today computers can't do. Computers can't experience emotions around artwork. Computers can't offer interpretations of artwork based on their own experience. They might go to Wikipedia and do some pattern matching and realize that this is an example of abstract artwork, but they can't offer an interpretation based on their own experience. And I think jobs that require empathy, jobs that require motivation, jobs that require emotional intelligence are jobs that we are going to have with us for a long time to come still. But I don't think this answer is really good anymore, because I think computer science is changing so quickly, and the ways the machines are helping us humans, they are changing so fast that I need to revise this answer every now and then. The advances we have with computer vision, the advances we have with all of the new stuff that is happening with neural networks and deep learning, they force me to revise the answer, and I think they force us all to revise these answers. Traditionally, I think we've thought that technology is about optimization, about efficiency, about reasoning, about prediction, about logical things. But I think the most interesting combinations are when humans and machines work together. Humans doing the things that we humans do well, machines doing the things the machines do well. But not saying that machines can't be creative, they are just creative in a different way. So final example. I come from Finland, and one of the most famous companies is called Marimekko. Marimekko is a fashion company that does these really bold patterns. There's a bunch of them here in Australia, stores for them. And the founder was a very visionary woman in the 70s called Armi Ratia. And Armi said that Marimekko could have equally well been a fun fair. It could have been a flower shop. She just chose the medium of making dresses and fabrics because that's the way she wanted to project her inner world. And Finland being a country of technology, Linus Torvalds, MySQL, Nokia, SSH, IRC, a lot of the tech stuff comes from there. I can't wait, I can't force myself not to think about what if Armi Ratia was a programmer? What would her world look like? So a few weeks back, I had this chance to experiment and try out things. So I went to Marimekko's Designathon, this event they did with their with engineers and hackers, and I collected all of their names of their clothes brands. So they have these very sort of particular brands like Joka Poika, Tasaraita, Kivet, Unikko, these very Finnish-sounding names. I'm glad you took the Finnish language here as an example in the beginning. And there was 1,400 names that Marimekko had generated throughout times. And I fed them to a recurring neural network that started to practice looking for patterns among those 1,400 names. And while the computers was crunching, I spoke with the Marimekko, sort of the creative team, and they said, no, this is part of the DNA of Marimekko. This is the stuff that humans are really good at. Computers will never help us with this stuff. Computers help us with this logistics. Computers help us with accounting. Computers help us with managing retailer relationships, but coming up with names for things is something profoundly human. And after roughly 4 hours, I went to see what the machine had created, and the results were really horrible. First of all, they sounded like Estonian, a totally different language. They were things like valos, insö, päränlö, kulvean, ja they didn't sound right at all. But I figured that the computer is still a baby. It's still figuring these things out, so I let it run for a couple of hours more. And in the morning, I woke up at 4 a.m. It felt like Christmas morning and Tamagotchi at the same time, and I went to see what has the computer created for me. And the results were magnificent. There were things like pyyninpakka, putti, pukukka, tanohalti, tirkka, ruitintulla, and even though you would have never heard any Finnish in your life, you can kind of hear the joyful Karelian vibe these things have. And I could see the faces of the creative team go like this. Whoa, these are really good. Maybe the computer should help us name things. And I tell them that, oh, I don't think you're going to be out of jobs anytime soon. The computer came up with 7,000 examples, and I was needed to curate these things. But these are names that I don't think you would have been able to come up with your own, because there's no way that you could have taken the 1,400 samples and kept them all in your brain at the same time. I think this is an example of how computers can be creative in ways that we just don't realize yet, and be helpful in ways that we haven't thought about before. I think technology is far too important to be left only for technologists. And it's important that we get a more diverse group of people excited about these topics. And it requires us to pay attention to the way we're introducing computer science to a new generation of people, whether it's by new paradigms of programming like machine learning, or just by having a more empathic, more whimsical way of explaining the concepts in the first place. I wish to see a world of computer science that is a tiny bit more whimsical, tiny bit weird, has more room for people who don't fit into boxes. When I was a little girl, I really loved conjugating French irregular verbs. I loved Bertrand Russell. I loved knitting. And never did I realize that all of those things are things that computer scientists are really good at often. Like conjugating French irregular verbs requires pattern recognition skills. Knitting instructions are basically algorithms. And Bertrand Russell is the philosophical father of a lot of the programming languages we know today. And I wish we were able to show a more diverse group of people who create this world, because the history of computer science is full of these people who have these diverse skill sets. The reason our industry has advanced so quickly is because we people contain multitudes. We can be many things at the same time, whereas computers can only be binary, one thing or the other. So Claude Shannon, as mentioned, was the guy who came up with the modern transistors, or the sort of precepts for modern transistors. He was a philosophy undergrad who fell in love with electrical engineering and math. I just learned that George Hinton's, the guy who is behind all of the deep learning advances today, his grandfather's grandfather or something like that was George Boole, the guy who came up with the Boolean logic. And you can almost tie a direct route to Aristotle and sort of the basis of philosophy and art and Greek legacy there. And finally, the very first programmer in the world, the daughter of a mathematician and a poet, Ada Lovelace, who lived in this world of where everyone else thought that a computer is a calculator, and Ada was the first one to realize that a computer that numbers can represent logic, and with logic you can represent anything in the world. So I think the reason why our industry is where it is today is because we have a lot of creativity. But in order to keep it moving, we need to attract more people who think differently. I think technology is built on humanity. And the very first computers were humans. They were people who were really good at calculating long series of numbers at a time when there were no calculators. And in some ways, I believe the very last computers, again, will be humans. And if we think about technology, in order to understand where technology is going to, we need to understand where technology came from. Today, when we think about technology literacy for kids, we think about coding, we think about social media skills, but a few years ago, technology was a combustion engine. A few years before that, technology was a bicycle, and being technologically literate at an age of a bicycle probably meant being able to build a bicycle or ride a bicycle. And we don't know what the technology of tomorrow will look like, or what the literacy skills look like. But we can look at the definition of technology, and it comes from Greek. And it states that technology is tools of problem solving. But not only the tools, also the skills and competencies and attitudes that us humans bring into the problem solving equation. So technology is profoundly human. Those two are interconnected. And unfortunately, we adults tend to forget this, but luckily the kids remember. I surveyed a bunch of 9-year-old kids in the Helsinki International School, and I asked them to define to me, what is technology, who uses technology, and what is it used for? And my favorite answer comes from this little girl, 9 years old, who says that technology is electricity that loves. Can we just pause there for a moment, because this is the most poetic thing I've ever heard. Technology is electricity that loves. It is used to play. I use it to have a conversation with my mom. We use a WhatsApp application. And then finally, and probably most importantly, people uses technology. Thank you very much.